In this session, I'm going to discuss some of the features Amazon DynamoDB customers are using to deliver an optimal experience for consumers of their own products and services. My name's Pete. I'm a specialist solution architect for the Amazon DynamoDB team. I've been with AWS around 4.5 years now. Excited to hear or to share some of these features with you. I made a presentation very similar to this for reInvent of 2020. We announced a lot of new features recently, and so I'm giving this updated session to expand on the options that you have. So the topics that I want to move through in this discussion are elasticity, the throughput and storage that DynamoDB provides for you, caching, backup, and restore. Essentially, this list of features, things that you can use to improve the experience for your developers, to rapidly innovate, and to deliver a better quality of service for your own customers. First up, let's talk about that elasticity around scaling. It applies to both throughput and storage. With DynamoDB, that's really the two fundamental ways that we measure your consumption of the service. In 2012, when the service went GA, we had an initial capacity mode called provisioned mode. In this mode, storage scales automatically. You only pay for the storage that you're using at the time in gigabytes at a 1 hour granularity. We also allow you to essentially describe or provision the throughput that you want for read units or write units. They're basically like two dials. You can change that to whatever you want it to be. And the DynamoDB service will scale out your tables partitions in the back end to support that level of throughput. In June of 2017, we added an ability to auto scale that read and write capacity based on CloudWatch metrics that tell us about your read and write unit consumption. In 2018, we added an entirely new capacity mode called On Demand. Again, the storage scales automatically, but the throughput scales instantly within 2 times your prior maximum consumption level, your high water. And in this mode, you don't have to give us any signal about how many reads and writes you anticipate using. And we also don't have to be watching your CloudWatch metrics to determine when and how to scale out. In this mode, you also pay per request, so you're always at 100% efficiency. Let's take a look at how that looks in terms of DynamoDB. In this graph, we can see some throughput consumption in green. The x-axis is time. In red, we see the throughput potential of the table, which is really determined by the number of partitions. And the same is true for provisioned mode. These partitions are basically the storage nodes across which we are distributing your data. We can see that as the load grows and nears the maximum, DynamoDB recognizes that the table might need more throughput potential. Partition splitting occurs, and we now have a new maximum. The load again reaches a new peak, and DynamoDB again splits partitions to increase the potential of your table. Each round of splitting can take around a half hour, but typically much less than this. Each partition is continually analyzing the throughput it is serving and the way your traffic is distributed across the data, and it makes intelligent decisions based on this. Notice that while our load sometimes drops to 0, the potential of the table never decreases. We're not paying for any consumption or any provisioned level of throughput, but when the load returns, our on-demand table is instantly able to cover it with 100% utilization efficiency. On-demand throughput sounds quite magical, doesn't it? There is some infrastructure associated with delivering this experience, and that is built into the pricing for on-demand capacity. Currently, you can read 1 million 4 kilobyte items with strong read-after-write consistency in US East 1 for 25 cents. There is a tendency for some to compare this to the pricing of provisioned capacity, and to conclude that on-demand is comparatively expensive. In making the comparison, an assumption of 100% utilization efficiency is often made for provisioned capacity. But this is rarely achievable. We offer the choice of capacity mode because load patterns vary, and so do business priorities. I am often asked how to choose a capacity mode. Before I dig in on that question, we should distinguish between price and cost. Price is what we charge customers to use the service. Cost includes the time of your technical resources. Adjusting an auto-scaling policy and smoothing things out to get best utilization in provisioned mode takes time. and should be checked and maintained periodically. Recognize that this is time that could potentially be spent working on things that deliver greater value to your customers. Reducing complexity in operations also minimizes risk and tends to improve availability. Some customers I've worked with have a large number of DynamoDB tables supporting a multitude of microservices, many of them being very low throughput, perhaps even development or test environments which see only sporadic activity. I encourage customers to establish a threshold for throughput spend. Maybe for you, it's $500 a month. If your table would consume less than this threshold in on-demand mode, simplifying your operations is likely worth the price. Additionally, consider the life cycle of your data. Perhaps you have tables sitting around and you need to keep the data, but you aren't actively reading or writing. The minimum for provisioned capacity is 1 read unit and 1 write unit. You can eliminate that throughput spend by switching to on-demand. We believe that on-demand capacity is the right choice for most DynamoDB tables. Prioritize the time you spend developing and maintaining optimal auto-scaling policy by spend. It turns out that mature workloads tend to have more predictable load patterns. On this slide, we see a few different throughput consumption patterns. At top left, we see consumption that might be one of those sporadic use dev or test tables. This is a slam dunk for on-demand. At bottom, we see what is likely a significant load. It might be a mature use case, and it has a fairly predictable seasonality. This looks very familiar to me. It could easily be the diurnal pattern of traffic that a customer like Amazon.com might see in a particular market. You can see that in this case, the provision capacity in blue is auto-scaling very nicely indeed. It's worth spending the time to dial in a policy for such a workload. What about the consumption pattern in the middle? This is interesting because there's some load that follows a predictable pattern, along with some sporadic and irregular spikes, which go well beyond the norm. These look very unpredictable and short-lived. If we cannot smooth them using queue-based load leveling, caching, or similar, on-demand capacity will likely be the most cost-effective choice. In provisioned mode, we'd likely need to maintain a minimum provisioned throughput level that can accommodate these spikes throughout each hour, every hour, and that may result in higher spend. One last note, it's easy and non-disruptive to switch between the capacity modes. We have customers who switch to provisioned mode to build out a new high water for maximum throughput ahead of an expected event, which will deliver a step function increase in traffic. And they switch back to on-demand for variability during and after the event. Please use these capacity modes to best balance price, costs, and service to your customers. All right, let's move along to caching since I just mentioned that. The DynamoDB Accelerator, or DAX, is a fully managed, centralized in-memory caching solution for DynamoDB data operations. It deploys as a cluster of instances in your VPC and is then available to clients within the VPC in accordance with an IAM policy. DAX is fully API compatible with DynamoDB, so clients need only initialize a session using the DAX driver instead of the normal DynamoDB SDK session initialization. From there, all the regular DynamoDB API actions and SDK functions for data operations are the same. DAX is a read-through cache, which means your client does not need to manage populating the cache on the side. You can write through DAX, in which case your writes are synchronously passed through to DynamoDB in order to automatically update the cache with any mutations, or you can write around DAX and just rely on the next read through DAX to populate the cache. Strongly consistent reads are also passed through DAX, and they do not update the cache. The cached data is expired according to a configurable time to live, and it will also apply a least recently used algorithm to evict oldest data from the cache if it fills. We recommend that production use cases always deploy with at least 3 nodes in the DAX cluster, distributed across 3 availability zones in the region. You can scale out up to 10 nodes to serve additional read traffic, and you can scale vertically by node type for higher write activity, larger cache, and greater CPU capability. While DAX in a 3AZ configuration is highly available, we recommend that you build your application workflows to allow for configurable fallback to work directly against DynamoDB should you need to restart or replace your DAX cluster. The benefits for caching can be significant, but an overloaded or unavailable cache can cause many cascading effects within a complex microservice architecture. So plan ahead and build in levers. Follow operational best practices for monitoring and scaling your cache. There's an excellent article in the Amazon Builders Library called Caching Challenges and Strategies, which I highly recommend. Many customers using DAX also employ additional layers of caching throughout their architecture. This could be a small local cache within the compute layer for the application, or within CloudFront, API Gateway, etc. For read-heavy workloads, a properly configured DAX cluster can offer very high cache hit rates, reducing DynamoDB's already low latency to sub-millisecond. It can drastically reduce the number of read units consumed for the DynamoDB table or secondary index, thus lowering your bill, perhaps enough to more than cover the price of the DAX cluster. And finally, it has the effect of smoothing the distribution of traffic across items in your DynamoDB table. The diagram here shows this effect, where items which are running hot do not see notably higher reads against DynamoDB itself. This can be a great operational benefit when your traffic is unexpectedly skewed towards a small subset of your data. It's not recommended to build around this for known hotkeys. You can expect that a single item under 4 kilobytes in size can be read from DynamoDB with eventual consistency up to 6,000 times per second. If you know you'll need to read it 20,000 times per second, DAX might help. But if DAX should be unavailable for any reason and your application falls back to reading directly from DynamoDB, you will see throttling and potential customer impact. For such a known hotkey, you can consider writing the same data under 4 different partition key values and having the application read from one of the 4 randomly. Such a configuration will still benefit from the cache, but will sustain the required traffic even when reading directly from DynamoDB. Disney Plus presented their use of this strategy in a recent reInvent session. So to summarize, for a read-heavy workload which tolerates eventual consistency, you should consider the potential benefits of DAX. Lower latency for a more responsive experience to delight your customers. Smoothing of unanticipated skew and pressure to parts of your dataset. And less read unit consumption in DynamoDB. With high enough cache hit rate, this can easily result in a lower overall AWS bill. Right, let's cover some backup and restore features. DynamoDB provides 2 backup features, one which allows you to snapshot your table and indexes and keep that snapshot indefinitely. And the other, point-in-time recovery, is the feature that I really want to cover in this session. Point-in-time recovery keeps 35 days of your table's history available for restore, so you can fully recover your data to any second in the preceding 35 days. We recommend enabling point-in-time recovery for all production tables storing data which is not ephemeral or easily recreated. Point-in-time recovery uses none of your table's throughput and has no impact to your live data operations. Back in my earlier work experience, one of the reasons I kept backups was because I worried about potential for losing multiple disks in an array at the same time and similar catastrophic infrastructure failures. That's really not the concern in the case of DynamoDB, but there is still a possibility of accidental or malicious table deletion and corruption of the data. This could be as simple as deployment of new code, which inadvertently writes incorrect data to a number of the items in your table for a week before the error is detected. Access to a DynamoDB table is denied by default, and best practice is to allow access according to the principle of least privilege. Fine-grained control to items, even per attribute, is available via your IAM policy. And the various data operations can be allowed or denied based on a number of powerful conditions. Despite all of this, it's possible that a malicious individual could delete a table or modify items. Such a scenario could also be the result of simple human error or a coding error. How might this impact your application or service? How would you recover? And how long would that take? Here's what the restore might look like in the DynamoDB console. You can see that I must name a table to restore to, and that table must not exist. I get to choose any second in the 35-day window to restore from, and I can choose whether to restore with or without my secondary indexes. If the application is being taken down during the recovery, it might be possible to delete the original table and restore to the same table name. But it's very much more likely that you want to keep the original table and possibly keep operating in a degraded state during the recovery. So you'll choose a new name for the restored table. Something like sense of relief might be appropriate. Now, if you've made the table name configurable in your application, you can roll your operations into the newly restored table. Or you could roll out updated code, which builds in a comparison against the restored table items each time you access an item in your live table. Sort of a repair on access procedure. You could also search through the restored table and make a comparison to the live table as a backfill type of approach. Lots of possible paths here, and which is best will be specific to the use case and the recovery scenario. DynamoDB Streams might provide an additional option. Capture your change data with new and old image, store it in S3, and query it using Athena. Something to consider. When you're defining your schema, think about building in attributes which can be used to determine items to be rolled back. This might be a timestamp, or it could be a version number for your application software. When considering data protection and disaster recovery, we generally want to define a recovery point objective. How much data am I willing to lose in restoring service? And a recovery time objective. How quickly can I recover? With point-in-time recovery, RPO can be 1 second. RTO will vary. A table restore takes some time. But see our recent announcement about improvements around shorter and more consistent time to complete a restore. As discussed on the prior slide, how you manage your application through a recovery is use case specific. Ideally, we would all have a full set of runbooks for various scenarios, but it turns out that business continuity and disaster recovery can be difficult and typically not frequently tested. I would suggest that no matter how prepared you are, having point-in-time recovery enabled will give you options that you may be glad to have in your back pocket someday. You should consider the value this adds for the critical business functions you build around DynamoDB. One more thing to note before I move on, when a table with point-in-time recovery is deleted, the point-in-time recovery data is also removed. However, before deletion of such a table, DynamoDB will automatically capture an on-demand backup of the table, as it existed at the time the deletion request was made. This backup data is retained for 35 days and is system-owned. It cannot be removed before this time is elapsed. You might like to make a policy of enforcing point-in-time recovery enablement on all important tables. AWS config may help here. And deny point-in-time recovery disablement attempts via IAM. Monitor CloudTrail for denied requests to delete DynamoDB tables and denied requests to disable point-in-time recovery. When it comes to your critical production tables, paranoia is a very good thing. All right, a new feature that I want to cover really quickly is export to Amazon S3. This was released just a few months ago, and it basically allows you to recover from your point-in-time recovery backups into S3. You name a particular bucket that you're interested in using. You get to choose the output format. That can be either DynamoDB JSON format or Amazon Ion format. And in both cases, the output will be compressed objects in S3. So you can choose any second in that point-in-time recovery window, typically 35 days. And this functionality is really nice because we've seen a lot of customers who have some kind of regular ETL process where they want to export the data. And we had some tooling to help accomplish that. We have Glue and we have data pipelines. But this provides you an ability to actually make the export without scanning from your actual live operational table. It consumes no read units. There's no additional load on your table. And it takes advantage of that point-in-time recovery data. So if you weren't aware of this feature and you do have some kind of a workflow where you are exporting your table data to S3, take a look at this. It will probably be much easier for you. Another great new feature is particle support. Particle is a open source query language, which is SQL compatible, but builds in support for various levels of structure in your data right from the start. And what we've done here is, because many customers told us that something that slowed them down when they wanted to build around DynamoDB, because many of them are familiar with SQL but not familiar with the DynamoDB APIs, they wanted to be able to describe their data operations using something that they were familiar with. So using the particle support in DynamoDB, you can now do that. As you can see in the example here from the new console, you can execute these queries against your DynamoDB tables. It's important to note that this doesn't magically turn DynamoDB's indexing into something that supports complex ad hoc reporting types of requirements. But what it does allow you to do is do the same kinds of indexing and data operations as DynamoDB supports naturally, and to describe it in a SQL form that's familiar. So as I mentioned, Particle is an open source specification, and it's meant to really be able to be used across many different data stores. You'll see support for it in a number of different AWS services. We wanted to add this for DynamoDB also to provide a nicer end-to-end experience for our customers. It's essentially implemented with 3 new DynamoDB API actions: execute statement, batch execute statement, and execute transaction. And it supports statements including SQL verbs of insert, update, select, and delete. So you can build a particle statement, which you then provide to DynamoDB using that execute statement API, and that will make the particular queries that you're looking for. If you want to be able to batch those queries, you can use the batch execute statement API action. Or if you want to do that using DynamoDB transactions for multi-item atomicity and also for the item potency guarantees that provides, you can use the execute transaction API. So this is actually really new and exciting. We think that this will really help developers to learn to adopt DynamoDB more quickly. Check it out. Multi-region architectures. So here we're talking about the global tables feature, which allows us to provide a service managed means for replication between DynamoDB tables in multiple regions. The table in each region operates like any other DynamoDB table, delivering high availability via storage in 3 availability zones. The normal DynamoDB regional endpoint is used to access the global table regional replica in that region. There's a 4 nines SLA on availability in each region, which extends to 5 nines when you build around a global table configuration. Replication between the regions is eventually consistent and multi-directional. The service takes care of all conflict resolution via a last right wins policy, and many customers use global tables to enable them to fail their application between regions, allowing them to achieve a higher level of availability. Others are primarily looking to provide a low latency experience for users who may be located in multiple geographic regions. Global tables can also provide a means to meet regulatory requirements. So what does a multi-region architecture backed by a global table look like? There is sometimes a tendency to imagine a scenario where an application stack deployed in US East 1 might want to fail over to a different region of a global table in the event that there is a DynamoDB service impact in US East 1. In fact, the multi-region architectures we see around global tables involve a complete application or service stack in each region. A failure could result from any part of the stack. A complex system of multiple components is far more likely to see a failure than the DynamoDB endpoint within a region. Here's an example where a customer application is made up of 3 different microservices. They decide to operate in both US West 1 and US East 1 to give lowest latency for users on both coasts, and to allow for continued service should there be impact to one of the microservices in either region. Everything looks good here, but then something goes wrong in microservice C within US West 1. This might be due to a regional problem in one of the AWS services that microservice C is built on, or it could be due to a software problem in a new deployment of microservice C. In any case, our metrics and alarms are telling us that there is a problem with microservice C in US West 1, And microservice A and microservice B are seeing a high error rate when they call microservice C. Based on this, we fail out US West 1 and we direct our West Coast users to the application stack in US East 1 instead. How do customers manage the flow of traffic for their application? There are many options here. Depending on the data operations required and the business requirements around the multi-region storage, a customer may choose to run all reads and writes to a single region. An active-passive configuration, which gives them the option to scale out the application in a standby region when required. This is the simplest approach for business continuity and disaster recovery, and it is easy to reason around matters of data integrity. Another option we see customers choosing is to make all writes and strongly consistent reads in a single region. But for eventually consistent reads with lowest possible latency, they read from their closest region. This is also easy to reason around in terms of data integrity. To me, the most interesting architecture is an active-active configuration, where reads and writes are made in multiple regions. If your data operations are idempotent, such as an append-only table or unconditional updates, this is easy to achieve. Due to the eventual consistency of global table replication between regions, we need to be more careful when using conditional flows. The conditional writes in an optimistic locking pattern, or a multi-item transactional read. We need to be careful to make all write operations behind these activities in a single region. Note that this doesn't necessarily have to be applied at the full table level. It really applies by item. For many business needs, it's possible to pin items to a particular region. Some items might be homed in one region and others could be homed elsewhere. Perhaps the primary key is named according to a prefix, and IAM can allow or deny write activity in the region based on this. Or you can maintain an attribute in each item which indicates the home region, and your write operations can be conditioned on this being local. You may be able to carefully rehome items. Imagine a user profile for a mobile game. The user might normally be in the US, but perhaps took a flight to Europe to vacation. Their user profile item might be rehomed to follow them. Or you might forcefully rehome items for a particular region if you need to fail out of that region. These are application level workflows, and it's exciting to consider the possibilities for each particular use case. Most traffic distribution requirements are solved with either manual or automatic changes to domain name records using Route 53. Depending on your use case, you might be able to leverage health checks and use routing policies based on latency or geolocation. If DNS is not reactive enough for your needs due to potential for client caching, you might like to look into Global Accelerator. It can provide latency benefits also. And finally, if you have something like a mobile application, the client could potentially access DynamoDB endpoints directly based on Route 53 policy and could use federated authentication and fine-grained access control to limit access. In such a configuration, I might recommend architecting with API gateways serving the client instead, as this allows for rate limiting and caching. Take a look at API Gateway's integrated DynamoDB support. For an example of global tables implementation, again, check out Disney Plus's presentation from reInvent 2020. All right, some more new functionality that I'm excited to share with you around streaming of change data. So in DynamoDB, we have always had change data capture, or we've long had, through DynamoDB streams. Essentially, every mutation in your table, an insert, update, or delete of any record is going to be reflected in that DynamoDB stream. And DynamoDB streams offers strictly once, always complete, and strictly ordered by updates for a particular item, ordering in the stream. You can then process from the stream using the Kinesis client library. It's compatible with the KCL. Or you can use a triggered Lambda function to poll for changes off of that stream and process them accordingly. So we see a lot of different use cases around this: event-driven processes, replication if we wanted to, pushing things into S3, perhaps if you wanted to maintain a complete log of all changes. One of the things that we noticed was that many customers were actually using a triggered Lambda function and then reading from the DynamoDB stream only to then place it back in a Kinesis data stream. And this could be for ease of integration with things like Kinesis Data Analytics, or to then feed into Kinesis Data Firehose. Or it could just be that they wanted additional clients and to be able to have some fan out there. So rather than let customers have to solve for that themselves, we've recently announced support for change data capture into a Kinesis data stream directly. And this can be configured for your DynamoDB table independently of DynamoDB streams. So you can actually enable both of these features. So this makes things very much easier to capture all of your updates directly to Kinesis. It also means that you can have a single Kinesis data stream where perhaps you're capturing the changes from multiple DynamoDB tables and perhaps even other event sources. One of the very common patterns that we see for use of streams is materializing additional indexes, additional views in different technologies. And this is often in this kind of a pattern where we have command query responsibility segregation, where we have DynamoDB being our authoritative source for the state of our individual item, gives us that concurrency control, isolation, durability, all of the things that we want from an operational database. But we also want to be able to do something like full text search, for example, with something like Elasticsearch. Using this pattern allows us to provide the best possible indexing performance for the particular type of query pattern that we have. So we're basically able to build kind of a polyglot persistence model here. And many customers were solving this by using a triggered Lambda function to read the changes from the DynamoDB stream and then propagate those to additional indexes. Redshift is also a common one, or perhaps even to another DynamoDB table. We recently announced in preview, or the Glue team did, a feature called Glue Elastic Views, which is really meant to solve for this and make these kinds of patterns very much easier for customers. You could imagine a completely serverless and code-free solution to propagate ongoing change data from DynamoDB to S3, Redshift, and Elasticsearch with some optional filtering and transforms. These are described using, again, Particle. So this is going to feel a lot like a materialized view or a secondary index in a completely different indexing technology with functionality that's purpose-built for your query needs. Super excited about Glue Elastic Views. Please go check it out. Take a look at the preview information. All right. One more thing I want to touch on quickly is what we can do to help developers innovate faster. How do they build on DynamoDB? NoSQL Workbench is a standalone graphical tool for Windows, Mac, and Linux, available to download from AWS and use at no cost. When building a solution around DynamoDB, the Workbench helps to understand your data and data operations and allows you to iteratively refine your data model for optimal results. It is composed of 3 sections: the data modeler, the visualizer, and the operations builder. In the data modeler, you define your schema. For DynamoDB, the relevant schema elements are those that you will index around. And you describe your indexes, the base tables and the secondary indexes. Then you can go to the visualizer, insert some example items, and see how they look from the perspective of each index. While developing your design, you'll likely go back to the data modeler several times to refine your indexing. This is an iterative process made very much easier by NoSQL Workbench. When you think you are satisfied with your design, you can commit your visualization example data to a real DynamoDB table. This then enables you to use the operations builder to easily construct data operations using a graphical interface, test them against DynamoDB, and generate snippets of code that you can copy as a template for your own software development. This approach to building on DynamoDB is very productive and I highly recommend that builders use it as the basis for your DynamoDB solutions. Let's talk about some of the less obvious ways that I'm seeing the NoSQL Workbench deliver business value. Here we see a screenshot from the visualizer. It's an online bank scenario that I've used to demonstrate DynamoDB transactions. The first thing I want to point out here is the button that allows us to commit our example data and indexes into DynamoDB. This not only enables the operations builder as the next development step, it allows us to very easily create a live environment for testing or for demonstrating the data model we're proposing, using the console, CLI, or SDKs. Next, I want to point out that the import and export buttons are up in the top left. These allow us to save out our data model and example data as a simple JSON file. This can be shared so that people can collaborate on the design and suggest changes. It can also be saved as documentation. Years from now, when the development team has changed, this will be easy to import to NoSQL Workbench to understand the model and perhaps to evolve the design to support new features in your application. Finally, notice the Export to PNG button. This allows us to easily snapshot the various views of our example data through our indexes. Again, this is terrific for demonstrations and documentation. When I'm working with AWS development teams and external customers to review the DynamoDB designs they'll use, this tool is priceless. Teams use this to develop a proposed model, they share it with others for review, and they save the designs out for future reference. This tool unblocks DynamoDB designs and encourages the right strategy for getting great results from DynamoDB. I cannot recommend it enough. It's changed my life. All right, so that is all of the topics I wanted to work through in the session. I want to open it up for question and answer here and see if I can help address any concerns that anybody has about these features.